This next corollary will turn out to be very useful in the chapter about integrals, I say, but now it's also really interesting to study the behavior of derivatives. Namely, we can draw some nice consequences from the Lipschitz continuity property that we've just seen in the previous theorem. Okay, the first of them is maybe not too spectacular. If f is defined on some interval a, b to r, if it is continuous and differentiable on the interior, so on the open interval a, b, differentiable. So then f is a constant function if and only if f prime of x is equal to 0 for all x in a, b. Okay, if I had an audience now, I would ask, have we already seen this? The answer is no, we've only seen one implication. We've seen that a constant function has derivative 0, so we've seen this direction here, but we have not seen this direction. So if the derivative is 0, we do not know yet that the function is constant at this point. B, if we have two functions from a, b to r that satisfy these two requirements, so continuous and the restrictions to the open interval a, b, f, a, b, and g, a, b, are differentiable. If this is the case, and if we assume that they have the same derivative, if f prime of x is equal to g prime of x for all x in a, b. So what do we know about two functions who have the same derivative? This is something you know from high school, but now we will really prove this. If this is the case, then they only differ by a constant, which means there exists some c in R such that f of x is g of x plus c for all x in the interval. So two functions with the same derivative only differ by a constant, which basically geometrically would mean a different height, so to say. And of course the height of the graph kind of doesn't influence the slopes of the tangent lines. C. Now slightly different. Assume that we have a differentiable function on all of R. Assume that we have a constant, I will call again C in R, such that the following holds. F prime of x is C times f of x for all x in R. Ladies and gentlemen, this is the first ordinary differential equation that we are studying here. Basically, okay, this would technically also be one, but anyway, this is the first real ordinary differential equation. A differential equation is some equation that does not define the function explicitly, but that gives some relation between the derivatives of a function and the function itself. So this is kind of a textbook, really one of the first examples you see. And this is basically just some equation, some property the function needs to have. And it turns out that we can solve these equations. We can determine the solutions of these equations. Namely, if this property here is satisfied, then it turns out that f of x is of the following form. F of x is a times e to the power of c times x for all x in R. And this constant a, this is simply f at time 0, at the point 0. So this is the only way we can solve this equation. And as we shall see later on, a lot of examples of ordinary differential equations have unique solutions. This is something for Math 2 or Math 3. Okay, anyway, but this is kind of the first example that we can see. So this is, then we can find this. Okay, so all these things are really proven quite easily from this Lipschitz property. Namely, so first of all in A, as I said, the one direction, so if it's constant then its derivative vanishes. This was theorem 4.3 part A. Now the other direction. So if the derivative vanishes, then this particularly means that the absolute value of the derivative vanishes for all x in A, B. And this means that we can choose the Lipschitz constant 0 in this continuity property. So this means by theorem 424 that f of x minus f of y is smaller than or equal to 0 times da da da, but this doesn't matter because there's a 0 here, for all x, y in AB. But of course this can only be 0 if the inside here is 0, and so this means f of x is equal to f of y for all x and y in AB, and this of course means that f is constant. Okay, so this only, this really shows the claim. Part B, I'm already starting here because this only takes one line. We can simply apply part A. We can apply part A, but to an interesting function. To the function f going from, so capital F going from AB to R, f of x is simply defined as the difference of f of x and g of x. F of x minus g of x. Then we know, since the derivatives are the same, that this has derivative 0, so by part A it must be constant. And so this difference is a constant, which means that this holds. Done. Okay, this is a nice consequence here. Okay, part C is a little more work. We also consider a function with whose help we will solve this. We consider the function capital F going from R to R, and this time we define f as f of x shall be defined as small f of x times e to the minus cx. Okay, what's this good for? We know that f is differentiable by assumption, e to the minus cx is also differentiable as we've seen, so capital F is again differentiable, and by the product rule we can compute the derivative. So capital F prime of x is equal to f prime of x times the second factor times e to the minus cx plus f of x times the derivative of the second factor, and this one we've computed, this is minus c e to the minus cx. Now, if we factorize this and pull out e to the minus cx, this is simply f prime of x, and here we get minus c f of x, and the whole thing times e to the minus cx. Now you see why we did this, because we just simply assumed that this here is 0. This was the assumption of the of part 3. So this was our differential equation. So this here is simply 0. So again, we have a function which is whose derivative is 0. So by part A, there exists some a in R with f of x is a for all x in R. So in particular, we get that a is in particular equal to f of 0, and f of 0, if we just write this down, this is small f of 0 times e to the minus c times 0, so e to the 0, which is 1, so we simply get f of 0. So this a is indeed f of 0, f at value, the value of f at 0. Yes, okay, so that's 0. So this means yes, sorry. So we've seen that. So a, this is a. So final thing, a is f of x. So f of x is small f of x times e to the minus cx. And now we just multiply both sides with e to the power of cx and get that f of x is a times e to the cx for all x in R. So we've solved our first ordinary differential equation. Okay, that's a nice consequence. Okay, one remark. By this uniqueness here, I wanted to consider a special case, namely for this equation here. I want to consider that a and c are both equal to 1. So in this case, c would be equal to 1. Then a would be f of 0, but anyway, but if we can then, so if c is equal to 1, this would mean that f prime is equal to f. And so we would have some a in here where a is f of 0. And if I assume this number to be fixed as well, I want a to be 1 as well, then I get a unique solution. Namely, I get that the unique solution of this equation would be e to the power of x, if f is equal to 1. So this is, again, and this turns out that this leads back to basically the high school definition of the exponential function, namely of the real exponential function. By corollary 425, so with c equal to 1, it turns out that the exponential function, now seen as a real function from R to R, is the unique, so unique, that's the important part here, differentiable function f from R to R, which has the following properties. With f prime of x equal to f of x for all x in R, and f of 0 equal to 1. And so it follows by this part C that this is really unique. So actually, if you only consider real numbers and ignore the complex numbers, you can define the exponential function in this way. Okay, because this is kind of what's implicitly used in high school. Now, we are coming to an extension of the mean value theorem, the so-called generalized mean value theorem. And this now involves two functions instead of just one. Theorem 427. The generalized mean value theorem. Okay, fg are now two functions which both are going from a, b to r continuous, and both restrictions to a, b, and to the open interval a, b are differentiable. And I assume that g prime is always non-zero, so g prime of x is non-zero for all x in this open interval. Then the generalized mean value theorem says that there exists a psi in this open interval AB such that the following holds, such that f prime of psi divided by g prime of psi is f of b minus f of a divided by g of b minus g of a. Okay. This is really more general than the previous mean value theorem, because if we know that g simply be the identity function, g of x is equal to x, then here in the denominator we would just get b minus a, and the derivative of g of x is simply 1. So this denominator would also be 1, and we would get back the equation from the previous mean value theorem. Sorry for the sudden cut. I just realized after erasing that I said something wrong in the end of the previous clip, which I had to cut out. So, for the proof of this generalized mean value theorem, we will again use Rolle's theorem and derivatives from Rolle's theorem, but this time use a slightly more fancy function. Okay, namely, we consider the function h from a, b to r. H of x is g of b minus g of a times f of x minus f of b minus f of a times g of x. Okay, why? Because it works. So there's no obvious reason to take this, but we will see later on in a tiny bit that we can really indeed use this there. So again, these things in the parentheses are just constants, so we can basically see this is just some constant times f plus minus some constant times g. So this is again, h is continuous, h restricted to the interval from a to b, the open interval is differentiable. And now let's compute the values of h. H of a is g of b minus g of a times f of a minus f of b minus f of a times g of a. And if you take a look, we have f of a times g of a twice here with a minus sign, so this is missing, okay. Here with a minus sign and here minus minus with a plus sign. So these two cancel each other out. So what remains is f of a g of b minus f of b g of a. Okay, now we evaluate h at the other end. H of b is then g of b minus g of a times f of b minus f of b minus f of a times g of b. And this time we see that we have f of b times g of b twice. So here and there. Again, here with a negative sign. With f of b g of b with a positive sign. And here with f of b g of t here with a negative sign. So again, these cancel each other out. And so what remains is this here, which is minus f of b g of a. And the other thing that's remaining here is this times this. We have two minus signs, so plus. So this is f of a g of b. Okay, and if we take a look, this is the same. So h of a is equal to h of b. And so we see that the requirements for Royle's theorem are met. So this means by Royle's theorem, there exists some psi in AB with h prime of psi is 0. Okay, but what is the derivative? So 0 is the derivative of h prime. And if we take a look at h, again, this is just constant times f and g. So we just get the same constants, but with f prime and g prime. So this is the same as g of b minus g of a times f prime of psi minus f of b minus f of a times g prime of psi. Okay, so now we just need to reformulate this, and we see that we're almost there. So we just need to make a few arithmetic computations here and see that we can. Namely, since by assumption g prime of x is not equal to 0 for all x in AB. And now we can just use the Royle's theorem conversely. The Royle's theorem says if g of a is g of b, then we would get some position where the derivative would be 0. And, but if the derivative is non-zero, then the values of g at a and b cannot be the same. So by Royle's theorem, g of a is not equal to g of b, which means we can divide by g of b minus g of a, which is good news. Okay, namely, if we take this equation here, this equation implies, so we can just add this twice, bring this to the other side, so the second guy, and then divide by g prime of psi, which is non-zero, and divide by this guy here, and then we get that f prime of psi divided by g prime of psi is equal to f of b minus f of a divided by g of b minus g of a, and this is what we wanted to show. Okay. Now, what's the point in using this generalized mean value theorem? This is basically, doesn't have this direct practical applications as we had, but it's really useful in some other situations. Namely, we will use some nice computational rules that are helpful in some situations. The so-called rules of L'Hopital, or L'Hopital, cannot write Hospital, L'Hopital, the L'Hopital rule. Or L'Hopital's, sorry, grammar, L'Hopital's rule, like this. Okay, so, namely, this is a theorem that you might have encountered in high school. It's kind of very popular among German first-year students because they use this in high school often and want to apply this in all possible and impossible situations in university calculus classes, in my experience at least. So assume we have some two functions which are differentiable on an open interval, and assume that g prime of x is not equal to 0 for all x, So, and assume we're in one of the following situations. Namely, what we want to study is then the limit of f divided by g. And this is a theorem which gives us some kind of tool of computing these things. And we assume that we are in one of the following situations. So basically in a situation where we don't know how to compute the limit yet. Situations. First, both are going to 0. And we assume the limit for x going to a. No, let's call this 1. So I call this a small I here, 1 and 2. Both are going to 0. So the limit of the quotient would something be 0 by 0, and this is something we don't know. So this goes to 0 and the other one goes to 0. And the other situation where we have a problem is if both go to infinity. And here I will only consider the situation of going to plus infinity, because minus is just a sign that can be flipped later on. So if f goes to infinity and g goes to infinity, so then we would have the limit infinity divided by infinity, which also doesn't make sense. So yeah, these are the two situations where we don't know how to compute the limit. And now L'Hopital found out that we can compute this limit by derivatives sometimes. Namely, if the limit of the derivative exists. So if the limit of x going to a of f prime of x divided by g prime of x exists, then also the limit of the original functions exists. Namely, then the limit of x going to a f of x divided by g of x is the same as the limit of this quotient of the derivatives. And this gives us really possibilities to compute limits we otherwise couldn't, as we shall see in an example later on. But first we have to prove this. One more remark. There are analogous statements, so this analogously holds if we would go to the other end of the interval. So I will only consider now here we are going with x to the lower end of the interval. So analogous statement would hold if x is going to b, or in the case if we wouldn't consider the interval a, b, but some interval which is unbounded, we could also do the same if x is going to infinity or x going to minus infinity, and if one of these two things holds. So the limit in infinity, if they exist, so we can work with them analogously. And I won't write down the same, but give you permission to use this in the same way, because this is, like in the lecture notes, I've written a bit of how to see the other ones, and this is not very hard. Okay, let's prove these things. And this is now quite some work, and I will only prove the case 1 and just put the other one to the lecture notes because it's overly technical. So I will only consider the case of dividing 0 by 0. Case 1. Okay, now, since the limit of them is 0 in A, because basically also we know that they have a continuous extension to this interval with A included, so to the half-open interval. And so just for simplicity, we assume that f and g are already defined in A. So we consider them as functions f, g from a, b to r with a included, where they take the value 0. With f of a equal to g of a equal to 0. So just simplifying. Now, so what we want to study is the limit, and we want to go via sequences. Namely, we take a sequence xn, n and n, be a sequence in a, b, which goes to a, and we need to see what the f of the sequence divided by g of the sequence does. So sequence here with limit of n going to infinity of xn equal to a. So by the generalized mean value theorem, and this is what we can now apply here, so by the generalized MVT, mean value theorem, for all n and n, there exists a psi n, and now this psi n should be chosen between a and xn. So we just take xn and consider restriction to a xn to this interval, and then apply the mean value theorem in this setting. So we get some psi n in between, such that the following holds. F prime of psi n divided by g prime of psi n is equal to f of x minus f of xn, sorry, divided by g of xn minus g of a. But we've just constructed it this way that these two are 0 in a, so we just get the ratio f of xn divided by g of xn. Okay, so this is a nice property. So we see that psi n lies in between these two, and we see that xn goes to a, so we can apply the squeeze theorem. Namely, it's caught in between a and the sequence going to a. So by the squeeze theorem, the sequence psi n converges to a. But then we know that the limit of this guy here exists, because that was the assumption that the limit in A exists. And we've seen with the connection between limits of functions and of sequences that this particularly follows then that the corresponding part for the sequences converges. Before I say some more words that don't help, let me just write down the particular equations. So we've seen that if we take the limit of f of xn divided by g of xn, if we want to compute this limit, we can just use the previously obtained psi n. So this is the same as the limit of n going to infinity of f of psi n divided by g of psi n. And as I said before, since this limit exists, this is the same as the limit of x going to a of f prime of x divided by g prime of x. And this shows the claim. Since this was an arbitrary sequence, and so this is some number here, so we've seen that for every sequence this converges to the same value. And so, let me write this down. Since xn, n and n was arbitrary, it follows that the limit of x going to a. I haven't noted the theorem, I think. So this was the connection between limits of function and limits of functions evaluated at sequences. Limit for x going to a of f of x divided by g of x. This is the same as the limit as x goes to a of f prime of x divided by g prime of x. And this is what we wanted to show. Okay, so case 2, as I said, this is then in the lecture notes, because this is a bit technical. There we need some more methods, because obviously we cannot just take a continuous extension if something goes to infinity. So we need a different method. So this is contained in the lecture notes. Okay. And after erasing one more time, we will see a nice example of a limit that we can compute now with the help of L'Hopital's rule. Let's conclude this section by computing an interesting example, or basically a non-obvious example, so to say, where L'Hopital is used in a quite intricate way. Namely, we want to study the following limit, the limit of x going to 0 from the right, so for positive values here, of the following expression, 1 over sine x minus 1 over x. We see that if we go from x down to 0 with 1 over x, this guy is going to plus infinity. We see that here as well, because the sign is positive for small positive values, which means that this is going to plus infinity as well. So what we have here is basically infinity minus infinity, something which is just something we cannot compute like that. So we don't know exactly what is coming out of here. But as it turns out, we can really compute this. First of all, we make this a fraction, namely we make it a problem that we can tackle with L'Hopital, which we can't do at this point, or if it's simply displayed like this, because we cannot just simply compute these limits independently. This would be kind of the simplest solution would be to say, okay, let's do this like limit of this, limit of that, and do them separately, but no, this doesn't work. This, because to do such a computation with limits, you really need the convergence. And here we have divergence, so we can't say anything about kind of limit of a difference. Okay. Now, if we have some number x which is between 0 and pi over 2, and we are only interested in values of x close to 0, so small positive values, so this is interesting enough for us, then we have the following situation, because otherwise if we would be in pi over 2, of course, this wouldn't be well defined. Sorry, it would be well defined, sorry. What am I saying? No, sorry, my mistake. it's fine to go further, but this is the interval we need. So we only need for values close to 0, and this is fine to consider. And we do the following computation. 1 over sine x minus 1 over x. We just bring this into the same denominator and get that this is the same as x minus the sine of x divided by x times the sine of x. Okay, not very exciting, but this is now a quotient. And as we see, x is going to 0. If x goes to 0, x is going to 0. That's a tautology. But also if x is going to 0, the sine is going to 0. So this means this is going to 0, this is going to 0, and hello L'Hopital. So this is precisely the situation where we can apply this. But we need to make some further checks for this. So first of all, what we need for L'Hopital is the differentiability. So, and this is quite obvious because x and sine x are differentiable. So the numerator x minus sine x and the denominator, which I want to give a special name, I want to call it g of x times sine x are differentiable. And so as I just said, the limits are 0, so limit of x going down to 0 is of x minus sine x is 0, and the limit of x going down to 0 of g of x is 0 as well. Okay, so what we need to check to apply L'Hopital is that the derivative of the function denominator is non-zero at a certain neighborhood of 0. So the derivative of this can be just computed by the product rule. Namely, so g prime of x is first of all the derivative of x times sine x. So the derivative of x is 1, so we just get sine x, and the plus x times the derivative of the sine, which we have seen is the cosine. So we've seen that if we're in this interval 0 to pi over 2, there we've seen that the sine is positive. X is positive, obviously, and the cosine is positive as well. This is the reason why we need to stop at pi over 2, because then the cosine hits 0. But here we know that everything is positive. So in particular, this is non-zero for all x between 0 and pi over 2. Okay, so much for that. So we can apply L'Hopital. The assumptions are met. So we know that the limit of x going down to 0 of the expression we started with, so 1 over sine x minus 1 over x, that this is the limit of x going down to 0 of the difference of the derivatives, and the derivative of the numerator is obviously 1 minus cosine. 1 minus cosine of x, and here we have sine x plus x times cosine of x. So this is the same limit, assuming the limit on the right-hand side exists. So right-hand side, I will always abbreviate this with RHS, exists. Yeah, RHS, okay, yeah. So much for that. So we've got this limit, but if we take a look at this, what happens here? We know that the cosine in 0 is 1. So the numerator is again going to 0. So this means limit x going down to 0 of 1 minus cosine of x, 1 minus cosine of x is 0. Okay, what about the denominator? If x goes to 0, this guy goes to 0, and this is something bounded, and this goes to 0, so this expression here goes to 0 as well. So yeah, we're kind of, we went from a bad situation and got into a new bad situation. So here we again get limit of x going down to 0 of sine x plus x cosine of x is 0. Okay, this is, this is bad news, but this means we are again in a situation where L'Hopital might help. So we just want to apply L'Hopital again. Now, first of all, both functions are differentiable. And if I call this function here h of x, The derivative of the latter function here is h prime of x, which is, so first the derivative of this, which is cosine. And now here the product rule, this is 1 times the cosine of x plus x times the derivative of the cosine, which is minus sine of x. So this gives 2 cos x minus x times sine of x. Okay, so what we see now, and to apply L'Hopital again, this would be then the thing in the new denominator. If we now go to 0, limit of x going down to 0, h prime of x, this is obviously 2 times the cosine of 0 minus 0 times, irrelevant, so 0. And the cosine of 0 is 1, so this limit here is 2. It's not 0, and this is now the good news, because now we see that we are getting somewhere with L'Hopital. So this is not, this is non-zero, and since it is non-zero, we particularly know that this derivative, the limit is non-zero, so this means that close to 0, the function itself has to be non-zero. So, hence there is some delta bigger than 0, such that h prime of x is non-zero in this delta neighborhood of 0, so that h prime of x is non-zero for all x between 0 and delta, so in this open interval. So we're in the position to apply L'Hopital. We've checked all the assumptions, so we can apply L'Hopital, and I can't write L'Hopital anymore, sorry. So the limit is now the limit of this former expression, so 1 minus the cosine divided by sine x plus x times the cosine of x. This is now the limit of the derivatives here, so of x going down to 0. Okay, and the denominator, we've already computed here the derivative, that was 2 cosine minus x sine. And the numerator is easily derived, so this is a constant thing which doesn't matter at all. Then we need the derivative of the cosine, which is minus the sine, and this gets another minus, so we get plus sine over x. And we've seen this here goes to 2, we've already checked, and this goes to 0, so we get that this is 0 over 2, which is 0. So we've seen that this limit exists, so this limit exists, and going back via this way, the original limit exists. So we've shown that limit as x is going down to 0 of 1 over sine x minus 1 over x is 0. Okay, this was quite some work. But there you see that kind of sometimes you can use L'Hopital again and again, and it sometimes derive often enough until you arrive at some nice solution. Okay, so much for this. In the next section we will study higher derivatives, and we shall see that we can do quite a lot if we and about approximation of functions in there. See you in the next section.